We have an acid-base problem, or problem involving the acidity of a acetic acid solution. And they say the concentration of this solution is 0.20 molarity. Now, if it's not given the solvent as far as what it's dissolved in to be of a certain concentration, you assume it's water. So we'll do that for this. So we'll represent acetic acid as just this AA, and we'll put an H on it, the acidic proton. You say, well, how do you know it isn't an acidic proton? Well, because it's called acetic acid. So we're just going to go without the structure, represent the name acetic acid, and say this will be the one it loses to, again, being in water. You say, how do you know that is present? You don't, but most of the acids and base solutions that you'll consider are going to be in water. It's where we can. That's why we can use the pH plus pOH equals 14, because the water always has a relationship of OH to hydronium ion. That concentration, that rate, the amounts of each is set when it's in water. So there's some things that we can do in water. So most of our acids and bases are going to be presented to us in water. So here we go. We're in that water, and we're going to act as an acid and give up the proton. So we'll make that minus, and we'll have, of course, H3O plus. And again, I'm just going without the structure here, saying acetic acid has some proton, gives it to water, and we get hydronium ion and the conjugate base of acetic acid. And they're telling us the Ka is small, so we know not much of this forms. Most of it stays in the reactive form. It has not reacted with water. And they're wanting to know what the pH is. So they give us the initial concentration, so we can start thinking of the ice table. They tell us that it's 0.20 molarity, the big M. So we're noting, hey, we're using the ice table, and we're considering molarity values. We'll assume, again, water is excess, and it is, so there's not a formation of the conjugate base and hydronium ion, kind of just thinking of this problem theoretically. Of course, then it dissociates, some amount reacts. We have one of these with one of these makes 1, 1, so all of our coefficients are just 1. We don't have to say 2x or 3x in this one. Then, of course, at equilibrium, we have 0.20 minus x, and x, and we're moving on to the law of mass action with the approximation. So we're going to approximate that this x is small. It does not affect the 0.20 to any great degree. So we now just end up with x squared, this times this, and our 0.20. So now it just becomes math from this point on. So we're going to solve for x. And the way we're going to do that is we're going to take and multiply these two to isolate x squared, and then we're going to take, of course, the square root of the product of these two. So I'll do that on my phone. Moving kind of fast here, getting more comfortable with my calculator. I hope you are too. You want to become pretty comfortable with the calculator that you use in homework, and then bring that same calculator, of course, to the game, to the test. So I'm going to leave it as 0.001897, and that's the concentration of the hydronium ion. So what I'll need to do is take the negative log of this, because we know that P is, as far as an operator, pH is negative log of hydronium ion. So we have that concentration of hydronium ion. I just need to take the negative log of it. Okay, there we go. And it's the negative, so this turns out to be 2.72 is the pH if I take the negative log of that. And that's fitting because we know acetic acid, being an acid, drops the pH. So again, make sure it kind of makes sense qualitatively. Hope that helps. Bye-bye.